Detailed narration for each slide of the uploaded lecture presentation titled Author A.S. Bhattacharya. Slide 1, title slide. Text. This presentation explores the fundamental concepts of lasers, an acronym for Light Amplification by Stimulated Emission of Radiation. We'll dive into the physical principles, mechanisms of action, system components, key properties, and real-world applications. This lecture is curated by A.S. Bhattacharya. Key concepts. Text. Stimulated emission. Transition probabilities. Multi-level systems. Population inversion. The core concepts behind laser physics begin with understanding stimulated emission, the process by which an incoming photon prompts the emission of another coherent photon. Transition probabilities define how likely electrons are to jump between energy levels. In multi-level systems, more than 2 energy states are involved, often to achieve population inversion, which is essential for laser operation. Slide 3, full form of laser. Text. Laser. Light amplification by stimulated emission of radiation. The term laser stands for light amplification by stimulated emission of radiation. This highlights that laser operation relies on the enhancement of light through the induced emission of photons from excited atoms or molecules. Slide 4, relative transitions between 2 energy levels. Text, N1, E1 minus E2, KT right. Spontaneous emission, induced emission, downward induced emission. A21N2 plus B21N2U nu equals B12N1U nu. Narration. This slide deals with the statistical nature of transitions between 2 energy levels. N1 and N2 are the populations of lower and upper energy states. The Boltzmann factor relates them at thermal equilibrium. Spontaneous emission happens randomly, while stimulated or induced emission occurs due to an external photon. Einstein coefficients A and B govern these probabilities, and the energy density U nu of incident photons plays a role in these transitions. Slide 5, transition between energy states. Text. Statistical process, probability-based. Electron transitions between energy states in a laser medium are probabilistic. The chance of an electron moving up or down depends on energy input, quantum rules, and external stimulation. Understanding this statistical framework is essential for designing efficient lasers. Slide 6, population inversion. Text. Optical pumping, electron excitation, inelastic collision, chemical excitation. Population inversion is a non-equilibrium state where more atoms are in excited states than in lower energy states, crucial for laser action. This can be achieved by various means. Optical pumping uses photons. Electron excitation uses high voltage current. Inelastic collisions transfer energy between particles. Chemical excitation involves energy from chemical reactions. Slide 7. Basic laser system. Text, laser medium, external source of excitation, Fabry-Perot interferometer. A laser system consists of 3 key parts. 1, the laser medium, which provides atoms or molecules to amplify light. 2, an external energy source, like a flash lamp or electric current, to excite the medium. 3, the Fabry-Perot interferometer, made of partially reflective mirrors, forms the optical cavity to reflect and amplify light in a controlled path. Slide 8. Properties of laser beam. Text. Time and space coherent. Extremely monochromatic. Highly intense. Extremely directional. Laser beams possess unique properties. Coherence. All photons are in phase both spatially and temporally. Monochromaticity. The light is of a single wavelength. High intensity, due to photon accumulation in a small area. Directionality. Laser light travels in narrow beams, making it highly focused. Slide 9, examples. Text, ruby laser, Heine laser. Some classic examples of lasers include ruby laser, a solid-state laser using a synthetic ruby crystal. Helium neon, Heine laser. A gas laser known for its visible red light, excellent coherence, and stability. Slide 10, common types of lasers. Text, pulsed, continuous, gas, dielectric, semiconductor, tunable lasers. Narration. Lasers can be classified based on their operational mode and construction. Pulsed lasers emit bursts of energy. Continuous wave lasers provide constant output. Gas lasers use gases as gain media, e.g. CO2. Dielectric and semiconductor lasers use solid-state or electronic junctions. Tunable lasers allow frequency adjustment across a range. Slide 11. Applications of lasers. Text. Scientific, medical, industrial, communication, narration. Lasers find widespread applications. In science, they aid spectroscopy, holography, and nuclear research. Lasers are used for eye surgeries, dental work, and tumor removal. Industrial applications include cutting, welding, and surface treatment. Communication systems use lasers and fiber optics for high-speed data transfer. A PDF version of this narrated lecture